Okay, now the last little thing I did kind of got cut off, but I'm gonna back up just a little bit more. And actually I'm gonna zoom in just a little bit more because this thing just will not do what I asked it to. Okay. First of all, just an overview for projectiles. Motion in two dimensions. You have an X motion and a Y motion. We started off with a quiz where you estimate a few things that you actually measured in the lab, and we tried to answer a couple of questions. Okay, well, let's go back to the scheme. I kind of made a mistake by listing the equations in this form. Really, all we need is to understand that there are 5 Y quantities for any uniformly accelerated situation, and ideal projectiles are always uniformly accelerated. The acceleration is just the acceleration of gravity, which has only a Y component. Okay, anyhow, we have the 5 Y quantities. We just designate these as Y quantities by putting a Y on each one, except for T, which is the same for both X and Y quantities. For X quantities, we have these, and again, T being the same. These quantities look just like they do over here, except they're indicated by subscripts X or delta X, here by subscripts Y or delta Y. I've already talked about this point about what we know and how we can use this scheme. So basically, if we know 3 of these, we can find all. Okay, so if we knew any 3 of these quantities, let's say any 3 of the first 4 quantities, we could determine the time. So if we don't know enough to solve the X quantities, we know just one of these quantities. Let's take it back. If we know one of these 3 quantities, then if we know the time for solving this set of equations or reasoning them out for reasoning using the equations, but often you need the equations. Okay, over here, if you have any one of these 3, you can solve this one for the time, you've got it, because for a projectile, the X acceleration is always 0. Okay. So here's our situation. If we know 3 of these, we can find them all. We automatically know the acceleration in the Y direction. It's downward acceleration of gravity. Now, I don't say a negative G, I just say G downward, because your positive direction for some application, you might want to choose downward as your positive direction. Usually for projectiles, you won't, but you might. So I just say G downward. So if you choose downward as a positive direction, your acceleration will be just plain old G. If upward is your positive direction, then your acceleration would be negative G. Okay. For your X quantities, for an ideal projectile, you know the acceleration is 0. So you kind of automatically know this and this. No, meaning you only need 2 more quantities here to solve the entire X motion. Over here, you need only 2 more of these quantities to solve the Y motion. I already know this, any 2 of these, that tells you everything you need if you can reason it out and will use the equations. And preferably both. Okay, so you have T in common. So if you can solve either one of these for T, they give you something else that you can use the other one. So if you can solve the X motion for T, then you've got T and AY. You need only one of these 3 quantities in order to solve it. So the details, I would leave up to you. Now here we did work through a few details. I'll just recap. We started with initial velocity in the X direction. This initial velocity had only an I component, no J component, meaning V0X is this, V0Y is 0. And H is 20 meters. So if we assume that y is 0 down here, then you have your delta y. Or if you wish to say it, y of 0 equals y sub 0. Okay, what's your horizontal range? We easily calculate this. We know delta y, we know the y acceleration, and we know the initial y velocity. So we just easily use an equation. Usually the third or fourth equation of uniform accelerated motion. Again, with y subscripts. Solve that easily. We can get time of fall. We can then bring that back into the x motion. And we know the initial x velocity, 120 meters per second, acceleration is 0, and delta t is the delta t we got here, 2 meters. So we have an x velocity of 120 centimeters per second, 0 acceleration, so that velocity doesn't change. Multiply that by the 2 seconds. We get delta x, which will be 240 centimeters or 2.4 meters. Now we have the same information, again, just recapping. V naught is 120 centimeters per second height plus 40 centimeters per second J. Means vertical motion starts upward, goes downward. So now the time of fall is going to be much different. So we're going to have a greater x velocity, a greater range, a greater change in x. Because when we multiply our initial x velocity by the delta t, we're going to get the y information. We're going to get a bigger delta t, we're going to get a bigger delta x. That's why when you throw a ball, you don't throw it horizontally, you loft it a little so it stays near the wall. Quite a bit. Okay. So anyhow, we solved the y motion. And in this case, that's a little more complicated. If we use this equation, the third equation of motion, your y of t is going to be a quadratic in t, and if you're solving for t, well, you let y equal 0, so you find out the time when the thing hits the ground. You set this expression equal to 0. You get a quadratic equation. It has two solutions, and as we said, one of the solutions in this case will be positive, the other will be negative. Okay, positive solution is the one you want. It's going to take positive time for this thing to go up and come down. The negative solution actually has a meaning. If this thing had been at this position after being shot from the ground, so it's arced up here, and now it's coming back down. And of course, it's got this initial y velocity, so the arc is going to look like this. Then the negative time is how much earlier the thing that had to be shot in order to reach this position with this velocity. So there is a meaning to the negative solution, but we're not particularly interested in it at this point on this problem. Something to store away. Okay. So that's the scheme. If I can find right here. Yeah. We also, and this wasn't on the previous video at all. We also, I didn't have it on record. And this is actually, this is a trigonometry. It's got a circle. It's not the triple acceleration. So yeah, we did all that. What is the triple acceleration? Just sitting right here waiting for me. Okay, there we go. Okay, so now, just in a nutshell, doing this kind of quickly, but there are a couple of things you really want to understand, so you understand it when you see it in the text. Okay, we got angular velocity, omega. That tells you how many radians per second around the circle. So we're given an angle theta and a delta theta, some small change in the angle. And we think of what's the velocity of the particle when the position is theta. Well, when the position is theta, your position vector goes from here to here. I have drawn that as a position vector. could have, and actually it's probably not a bad idea. So here's our position vector. And here's position vector after we've moved through some angle delta theta. So delta theta is just the angle between these two vectors. Then our actually velocity vector of a particle moving along this circle is going to be tangent to the circle. Since we're moving at constant angular velocity, there's no acceleration, etc. Not going to get into that right now. But this velocity will be perpendicular to the r vector when the position is theta, and this velocity will be your velocity when the position is theta. Well, we get then these two vectors, and there's a difference in direction. There's no difference in magnitude because this thing's moving at constant velocity. So we can bring these two vectors down here and use the same initial point, draw the two vectors, and we see that our change in velocity is this little vector here. Okay, this vector is this one minus this one. That's this one's change in velocity. It's this vector minus this vector because this vector plus this vector equals this vector. Write that out and think about it. That's why it's your delta V. But the arrow from the tip of the first vector to the tip of the second, assuming velocity vectors have the same initial point, is going to be the change in velocity. Okay. Now, this little triangle here, I said, without drawing the arrows, just drawing this arrow, it's an isosceles triangle because both of these velocities are the same. So that this angle and this angle are equal. And first thing I want you to understand then is, as delta theta approaches zero, these angles being equal will have to add up along with this angle to give 180. So if this angle approaches zero, these two have to add up to 180. It's an isosceles triangle, so they're equal. So they each approach 90 degrees, which means that the acceleration is perpendicular to your velocity vector, which is perpendicular to your radial vector, the vector from the center of the circle out to the arc, but in the opposite direction of this vector. Okay, again, the acceleration vector, which is going to be your delta V over the time it takes to get from here to here. That's going to be your acceleration vector. And it's going to be perpendicular to velocity vector, but in this direction. So it's in the opposite direction to your radial vector. Since this vector is at a 90-degree angle with this, and this one's at a 90-degree angle with this. Now, a little thing about how fast this thing's actually moving. I've got omega A here. I haven't explained that. I've got a delta theta equals omega delta T down here. Why would I do that? Well, first of all, the speed of the vector, again, the vector velocity of the particle, the speed is omega A. Why is it omega A? Well, first of all, omega is your number of radians per second. That's the measure of omega. And 1 radian means 1 radius along the arc of the circle. Now, more specifically, it means a distance along the arc that's equal to the radius. So if the distance along the arc is equal to the radius, that puts the position going from here to here approximately. And that angle is a little less than 60 degrees, and you can work it out very easily. That's something you should have done more than once if you had a trig course and a pre-calculus course. And it's something you should be familiar with, but it tends to be a little confusing. I had a really good trig course in high school. I didn't get a pre-calculus course. So I jumped into calculus-based everything, and calculus, first day of class in my whole college career. And it was a little confusing, but it was good for my soul. It worked out. Okay. Again, 1 radian means 1 radius along the arc. So how fast are you moving along the arc? Well, if you're doing 1 radian per second, you're going to move at 1 radius per second. So if the radius is A, you go a distance A per second. Now, if it's 2 radians per second, well, then you're going to go 2 radians or twice distance A along the arc. And your speed will be 2A per second. Okay, whatever A is. In any case, you end up understanding that you just multiply the radius by how many radians per second, that is by how many radii per second you travel along the arc, and it tells you what distance you travel per second. All right. So also the arc, the distance you go through is omega delta t. That should be familiar with stuff we've already done. If not, ponder it. You get the delta t from omega and delta theta, and relate this all then to time and get the acceleration. Again, bottom line here, understand what a radian is and how a radian tells you that the speed along a circle is omega a. And in fact, these vectors have the same vacancy. Gives you a triangle with vectors here. That's isosceles, and that these angles as delta theta approaches 0 approach 90 degrees. And isosceles, it looks of recognition when I did this. Hopefully you've seen this before, you'll see it in your text. And it's kind of important to understand. In this chapter, which is on motion in 2 dimensions, 2 main things are projectiles and motion around a circle. Specifically, the idea of centripetal acceleration, which we're going to need as we move forward in the course.